Okay, what you should have seen so far on Canvas, going back to those week 1, day 2, day 3. You saw an introduction where I talked about how to get through Canvas, how to manipulate Canvas, what to see on the left-hand side. Then I showed you the syllabus, which I call this thing, okay, which has the date, what we're doing in lecture, what we're doing in lab. We went over extensively the course information sheet. And you should have sent me an email letting me know if there's something drastically in your path where you can't take the exam, the lecture exam Monday at noon and the lab exam Tuesday at noon. Okay. I don't know the results of that yet but by the time you were looking at this, I will have known, and I'll make the announcement clearly a couple times, and so will Brooke, that that's the way it's go ahead. Not because we're trying to be difficult for you or anything else. It's because you got 19 days to get through this. If you're taking the exam on Monday, lecture exam, Tuesday, lab exam, you've already gone through 9 days of those 19 days. There's only 10 days left. So we got to get you moving fast. Got it? Okay. So if you look at this, I'm going to bring it closer. That was the first lecture series. Let me get it closer. Introduction to the syllabus, metric system, we did the introduction. Now we're doing the metric system. Okay, and we're going to do a metric lab. And I'm going to do those for you right now. You saw that there was a D as in David, next to it. What that meant, directed teaching, the stuff that's on the board. Now that might be a little bit blurry, so get ready to write this down. It says metric system. Then it says 2 letters, S and I. S is in Sam, I is in Ida. SI. Then it says English/Imperial. Then it says base 10. Base, B-A-S-E, 10. Then it says units of measure. Units of measure. Then it says prefix. Then it says scientific notation. I'm going to talk about each one of those and check them off as we go through. 2 more over here. It says surface area and volume. This deals with the lab. Got it? Okay. Now, unfortunately, the camera works good, and I can move it remotely. I can't get it focused any better. If I move it closer, it focuses, but then you're too constricted in what you see on the board. Because I'm going to be writing stuff right there. Are we good? Okay. Okay. Here we go. I'm looking for my red. There's my red. There's not much in the red. Oh, well. Looks like I've been ripped. Oh, you know what? I think somebody put them in a drawer. There we go. No red. No red. I use a variety of colors. It's easier for you to follow it. No red. Oh, well. We'll make it work. Okay. Metric system. We talked about this in another video I did. When you have taken a science course, probably in high school or something like that, they should have introduced the metric system to you. And it was miserable because you had to learn all the conversions. For an example, a kilogram of weight is 2.2 pounds. So you had to know what all that was. And how many centimeters in an inch. And how many grams in an ounce, all that kind of stuff. We don't do it that way. The metric system makes total sense, and I'll explain why, because I'll give you some examples of it. But the metric system is what scientists have used from the dawn of time. And because the health fields are a branch of science, it's all about science, they use the metric system. There is no conversions. You don't weigh something in pounds or ounces and then turn around and convert it into metric system. You step on a bathroom scale, you look down, and the weight is in kilograms. You don't have to make any conversion. You look down, that's what you write it at. Got it? Okay. I'm going to go back here and I'm going to check some things off. I'll check them off. You won't be able to see that. That's why I like the red. I'm going to use the orange. We're going to be talking about the metric system. Okay? And now the next thing you see is SI. SI stands for, get ready to write this down, Systems International. Systems International. Okay? Now, I'm not positive of dates and stuff, but back during the Cold War, this is back in the 1960s, the main powers on this earth got together in a summit and they said, hey, look, there's going to be a time when we're going to take down the barriers around this world and different countries are going to be open to everybody. Okay? The wall, the Berlin Wall came down. Walls in China came down. Travel from one country to another became commonplace, and they knew that was going to happen. They said, so in order for that to happen, we have to establish a system of language so we can all communicate with each other, and a system of measurement so we can measure things. Okay? Now, I've traveled a few places, and I went to China. And when I got off the airplane, there was people there that spoke English. Not too good, but they spoke English. I've been to other countries. Mexico, they speak English. You get off the plane, there's somebody there that can communicate. Now in our country, you get off, we don't know what you're saying. That's because the language that they picked back in the 1960s to be the universal language is English. Okay? We already know how to speak that. For whatever reason they spoke English, whether it was straws or whatever, that was the established language. All countries agree to that. So when you go to China or Mexico or Russia, Spain, any of those countries, they teach in school the English language. So we do it as a secondary language. We said, oh, what language are you going to learn? I'm going to learn French, I'm going to learn German, or I'm going to learn Spanish. And we take that as our language requirement. And we take it for 4 years or whatever it is. They take it continuously. Got it? So it's part of the Systems International. International, I, System, S-I, International System of Language and Measurement. The International System of Language, English. International System of Measurement, metric. So when we came back from that summit, they went across the United States, they said, we're going to be changing our system of measurement from the one we presently have, which is called the English or Imperial System. English or Imperial System. The system of measurement of feet and inches and yards and ounces and pinches and tablespoons and all that kind of stuff. That's the English Imperial System. And it is outdated and it is dumb. We're used to it. You're saying, well, I use that all the time. That's because you were born with it, you're educated with that. Okay, but it doesn't make sense. Here's what I mean. How many inches are in a foot? You know, that's easy, that's 12. Okay, because you had to learn that, didn't you? How many feet in a yard? You know, well, that's it, that's 3. Second thing you had to remember. How many feet in a mile. Oh, that's like 5,280. Okay, there's a fourth thing you've had to remember. You get it? So, and all the numbers are different. Okay, how many ounces in a pint? How many pints in a quart? How many quarts in a gallon? How many gallons in a barrel? You see where I'm going with it? It's just all these numbers associated with different denotations. You had to remember, and you remembered them because you learned them. Okay? So you learned the English or imperial system. We subscribed to the Systems International, which is the metric system. Okay? We just didn't want to give it up. When you go to put fuel in your car in another country, you put it in liters. So when you look at it, it doesn't say how much is it per gallon, it says how much is it per liter. And there's not quite 4 liters in a gallon. Get it? So if they said, it's $1 a liter, you put in 4 liters, you put in $4 worth, your gallon of gas cost a lot of money, didn't it? Okay? My point. Science always deals with this. You will always, in the health field sciences and science, you will always deal with the metric system. Got it? And it's real simple. I'm going to go over the first 3 terms. We're talking about the metric system. SI stands for Systems International. That is metric English. English imperial system. That deals with the system of measurement that we use in this country that we're trying to get away from. And it says base 10, the next thing. Base 10. I want you to think about this. The metric system is based on the base 10. In other words, what that means is it takes 10 of one thing to make 1 of another. Or one thing is 1/10 of another. Does that make sense? We have one system that we use in the English imperial system that's based on a unit of 10. What is it? Pause. Hit pause. You think about it. Don't unpause it until you can tell me what it is. One system. Here's the question again. We employ one system in the English imperial system that's based on a unit of 10. What is it? Okay, now you unpause it and you said, I don't know what it is anyway. I want you to give me the answer. I get it. You're lazy. It's money. How many pennies does it take to make a dime? 10. How many dimes does it take to make a dollar? 10. You get it? It's very simple. And if you think about it mathematically, all you're doing is moving a decimal place. For an example, here is $1. That's $1. $1. Okay? If I put a decimal place here, it's $1. If I put a decimal place here, it's a dime. Remember, if you move it over, you got to put a 0 in to hold the base. That's a penny. You still see the number. It's $3. It's 30 cents. I'm sorry. I screwed that up. It's 30 cents. It's 3 pennies. You get it? The number still stays the same. In our inches and feet, that number disappears. So you never really know if you got the right answer. Got it? Okay. So you know what base 10 means. 10 of one to make another 1 of another, which is moving the decimal place. The number doesn't change in your eyes. It doesn't change from 2.36 to 5.72. Okay? How many feet in a mile? 5,280 feet. What happened to the mile? Mile was 1. Now you got 5,280 out there. The numbers don't even look the same. Got it? Base 10. That's what it means. 10 of one makes 1 of another. The number never changes. You just move the decimal. Got it? Okay. Now to learn the metric system, we're not going to make conversions. You have to know 2 things that you have to memorize. Units of measure and prefix. We're going to do units of measure first. Okay. Here's your units of measure. Okay? Units of measure. That's how we measure something in the metric system. Okay. If we're going to measure weight, we measure weight in our system, the English or imperial system. How do you measure it? Think of it. Weight. You say pounds right away. Good. What else? Tons. Good. Do you know there's a long ton and a short ton? A short ton is 2,000 pounds. Long ton is 2,200. We can't even make up our mind on that one. But what about smaller? What's less than a pound? I just told you. What's less than a pound? An ounce. Yeah, but I thought ounces was liquid volume. Oh, yeah, it is. So that means it applies to two things. You get where I'm going with this? Teaspoon, tablespoon. Those are all measures of liquid too. Quarts, pints, half gallons, gallons. You get where I'm going with that? So we have all these things rushing around our head. Weight. In the Systems International metric system, you weigh things only one way. That is in grams. Weight is only in grams. You see, yeah, I said, what's another way of measuring it? What's another way of measuring it? Pause it, pause it. When you come back, I want you to tell me what it is. Okay, now you unpaused it and you said, I don't want to know. I just want you to tell me. Okay, and some of you said, well, like kilograms, like milligrams. Okay, well, do you still hear the word grams in there? So when something comes in front of it, it's called a prefix. So the unit of measure is grams, but we added and did something to it to make it kilograms or milligrams, didn't we? Didn't we? So that means there must be something else in here. But the unit of measure in the metric system of weight is grams, and that's it. Nothing else. You weigh something, it's in grams. And we abbreviate it lowercase g. What about length? We measure it in what? Meters. Abbreviated lowercase m. I've seen it written in uppercase m, but I don't want you to do that. Okay? You say, but yeah, but what about kilometers and micrometers and centimeters and stuff like that? Hear the word? Prefix followed by meters, which means we measured length. Easy, 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 right? Okay. What about, now I'm going to say, they say volume, but I want to be specific at how we do it. I'm going to put liquid volume. Okay. Reason I put liquid is you can measure volume in length too. This room, for an example, length times width times height gives us volume, doesn't it? And that's going to be in, let's say, meters cubed. So in liquid volume, it's the old ounces thing. It's in liters. Okay? Liters. And it originally was a lowercase l. I see it written a lot with an uppercase L. You got to remember, in the United States, we kind of do the things we want to, and we modify things, okay? But originally, it was lowercase l, okay? It's not as critical, just so we know that it all follows suit. Yeah? What else do we measure? How about temperature? Okay, and some of you said Celsius. Absolutely. Well, what about centigrade? Absolutely, they both mean the same thing, okay? And it's a little degree sign, little zero, followed by a capital C. That's how we abbreviate it, okay? You say, yeah, but for some of you who've had chemistry, you said, what about degrees Kelvin? Okay. What they did is when you deal with high temperatures, pretty soon when you have a number out there like 258, when you have 2,563, you're going, man, that temperature, I don't even know what that is. That's just hotter than hell. That's what's going to happen when I go down below to visit my friends. They use Kelvin. So when they're talking about high clumps of temperature, they use degrees Kelvin. We're not going to use that in biology because we'll never see those temperatures. We're talking about body temperatures, Jocko. Yeah? Okay. So we have weight, length, liquid volume, temperature. Let's throw one other one in science that we use a lot. A time. And it's in seconds. And we abbreviate it lowercase s. Good? There's all kinds of other things. Okay? And if you really want to get into the metric system, you can look it up. You can type in Google and look at metric system, units of measure, and they'll give you things for measuring all kinds of stuff. These are the ones we use in the health field, in biology. We don't go too far outside that. Got it? Got it? So weight, grams, length, meters, liquid volume, liters, temperature, degrees Celsius, centigrade, time, seconds. Are we good? Okay. Okay. The next thing you see over here, I just did units of measure, didn't I? Now that prefix things, the kilo, the milli, the centi, the deca, hecta, all those things, those are all prefix. Remember I said there was two things in understanding the metric system that you were going to have to know. One is the unit of measure, and the other one is a prefix. I'm going to do the prefix for you right now. And what I'm going to do is I'm going to turn the camera a little bit that far so you can see the next column I'm going to write. Okay, so I'm going to move it over. And right there, I'm going to do the next column. And the next column is prefix. Okay. We're going to, now, for every time you move, remember the decimal place based on a unit of 10? Every time we move the decimal place 1, we change the prefix. Got it? So if we have milli, whatever, millimeter, we want to go to centimeters, we just move one over to the left. Get it? Okay? So when you move the decimal, you got to change the prefix. Unit of measure, never going to change. Unit of measure, never going to change. So I'm going to write a list of the common ones we hear in science and in biology. At the top of the list, we put kilo, followed by hecta, and I'll put in parentheses hecta, hecto. You see it written both ways with an A and an O. Then deca, D-E-C-A, D-E-K-A. I've seen it written both ways. Okay, then I'm going to put a squiggly line here. And in the course of explaining to you how to use the metric system, I'll call that the line. Okay. I'll put 2 of them because here's where your units of measure go. Right here, milli, liter, gram, seconds. That goes in here. How many of them are there? 1. Okay, and then we go below the line. So we're going to go to smaller stuff, smaller than those. And the first one is deci, D-E-C-I, then centi, C-E-N-T-I, and then we go to milli, M-M-I-L-I, no, M-I-L-L-I, milli, and then we skip a couple, and we go down to micro. And after micro, we go to nano. And then finally we go to angstrom. I know you can't see these, that's why I'm spelling it for you. Angstrom. Okay, got it? Deci, centi, milli, micro, nano, angstrom. Remember, every time you move a decimal place, there's going to be a different prefix goes with it. Now, I'm going to change colors for you. We'll do it in blue. Kilo. We abbreviate that, capital K. Hecto, hecta, capital H. See, big capital numbers. Deca, deca, D-E-C-A, capital D. Meter, liter, grams, seconds. That's written there for you. Deci, lowercase d. Now you see how important it was to get that uppercase, lowercase. Centi, lowercase c. Milli, lowercase m. Micro. Now this one kind of looks weird. It looks like a U, but on the front part of the U, there's a leg that goes out there. Okay? There's a long leg and then the letter U. Nano, lowercase n. Angstrom, kind of a weird one. It's a capital A with a degree sign above the top of it. That's how you write angstrom. Okay? And nano and angstrom, when I took sciences back when there were still dinosaurs roaming the earth, we didn't use those too much. We had to memorize them and stuff, but we didn't use them too much. But they came into play a lot when we started with the electron microscope and looking at viruses and bacteria, because they're down into nano lengths, okay? And then viruses, nano. And now we're looking at proteins, things that make them up. And we're getting into smaller things. So that became very popular, nano and angstrom. Got it? Now, I'm still not done with this list. I'm going to do some red over here for you. Kilo means 1,000. Hecta means 100. Deca means 10. Meter, liter, gram, second, 1. Deci, 1/10. Centi, 1/100. Milli, 1/1000. Micro, that skips. Remember I said we skip a few. Micro, because see, milli makes you think of million. No. Milli means 1,000. 1,000. Micro means 1/1,000,000th. Now, I don't want to put all those zeros out, is 9 zeros, and angstrom is 10 zeros. Do you understand? Okay. Now, what I'm doing is I'm showing you how you're going to make your conversions. I'm going to make it really easy for you. For those of you that have had Chem, whether it's Chem 1A or Chem 3A, you learn about cross cancellation, linear cancellation, right? And at the end, when you did this big linear thing and they say show your work, at the end you had so many zeros, didn't you? And that was how many times you're going to move the decimal place. I'm going to show you an easy way of doing it. Okay. Kilo, how many zeros do you see there? Answer, 3. That's a jacked up 3. 3. Hecta, how many zeros? 2. Deca, how many zeros? 1. Meters, liters, grams, seconds, how many zeros? None. Deci, zeros, just zeros. How many zeros? 1. Centi, how many zeros? 2. Milli, how many zeros? 3. Micro, how many zeros? 6. Nano, how many? 9. Angstrom, 10. Okay. Now, listen to what I'm about to tell you. You go up, you move it to the left. You go down, you move it to the right. And right now you're probably going, what is this crazy dude trying to say? I'm going to show you how to convert. Here's what I'm trying to tell you. Is if I put up a number, 2.35 meters, and I say convert it into centimeters. You know, well, how the hell am I supposed to do that? I just showed you the pattern. Okay? Now I'm going to give you some examples. So, you can't see that. I'm going to do it right here. Okay. Here's a number. 2.35 meters. Here's where I'm at. 2.35 meters. I want you to change it into centimeters. Okay? Now, for those of you who are doing linear cancellation and you figured it out and you got it right in chemistry, you keep doing it the same way. We're going to do it biology style, Knudsen style. Okay. Here's what you do. Change colors for you. This is meter, unit of measure. There's nothing next to it. There's no prefix. But there is a prefix here. So since there's nothing, 0 goes there. The number of zeros, 0. So you put a 0 up here. Centi is 2. 2 zeros. So you put a 2 here. The difference between 2 and 0 is 2. 2. Now, when you went from here to here, did you go up or down? You went down. Which way do you move? Which way is the arrow going? To the right. You move it 2 to the right. Get it? I'll put the answer in blue. So you had 2.35. You're going to move the decimal place 2 to the right. Your answer is 235 centimeters. So if you look at that, it says 2.35 meters is the same thing as 235 centimeters. Got it? 235 centimeters. That's it. There's no cross cancellation. There's no crossing out zeros. None of that stuff. You just go to your chart. Are you going to have to memorize that prefix thing, get things right? Yeah, it ain't too tough. It goes, if you look at the top, it goes 3, 2, 1, 0, 1, 2, 3, 6, 9, 10. Done. Okay? Write this down. Practice it a few times till you can do it without having to look at the answers. And then you've got your metric conversions done for the rest of your life. Good? Okay. I still do it this way. Okay? Now, what you want to be careful of is that you do not do a shortcut here. What I mean by shortcut, instead of writing it out, you try and do it in your head. You will jack it up. Let's do another one. Let's do another one. Let's do, I tell you what I'm going to do. I'm going to do 2.35 centimeters, and I want you to convert it into micrometers. Go to your list. What goes above centi? Centi. What goes above centi? 2. What goes above micro? 6. What's the difference between 2 and 6? Is 4. Did you go up or down to get there? You went from here to here. You went down. Which way does the arrow say you're going to go? Right. So you go 4 to the right. 4 to the right. So your answer is, I don't have it, I ran out of board. So it's 2, 3, 5. There you moved it over 2. You got to move it over 2 more. 0, 0. So it's 23,500. See, the number's still there. Okay, now I hope you're pausing this and going back and trying to do it instead of me entertaining you. If I do it, you're going, oh, I get it. Then what happens if I give you a problem? You're going, huh? Okay, let's do another one. So what I want to do is I'm going to put this number up here. I want you to do it. I want you to do it because it's paused, and then you unpause it, and you'll see if you got your answer right. Okay? So, get out the black one. It's always going to be the last one out. There it is. All right, here's the number. We're using the number 235. Okay, I use it 2.35, but let's say I use 235. There's an imaginary decimal right there. And I'll say that is deca. What was I using? Meters before? I'll use grams. And I want you to turn it into kilograms. Okay? I agree. I'm tired of changing that. What goes above deca? 1. What goes above kilo? 3. What's the difference between 3 and 1? If this is confusing, drop the class. Okay? 2. Did you go up or down to get there? Well, I went up. I started here and I went up here. So if you go up, you go to the left. You go 2 to the left, 2L. So it's 2, whoops, I'll do it here, 2.35. So there's 2.35 kilograms in a decagram, in 235 decagrams. You get it? That's it. That's it. Okay? 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 Now we're going to see. We're checking for understanding. I'll give you a number. The number is 0.0123. I'm going to make it milliliters, and I want you to convert it into deciliters. Okay? I want you to pause this, video, pause this recording now, and give me the answer. And go back to it. Don't do it in your head. Do it just like we have been doing. Pause it. Okay, now you unpause it because you should have an answer. So here's how you did it. What goes above milli? 3. What goes above deci? 1. What's the difference between 3 and 1? 2. Did I go up or down to get there? I went from here to here. I went up, I moved it to the left. There's your answer. 2 to the left. That means the answer is going to be 0.000123. Got it? Got it? Okay. There's one little catch to this thing. One little catch. Just bear with me because it's not that big a deal. If you stay from the line above, what's the difference? If you stay from the line below, anything below it, it's the difference. Line above or anything above it, difference. Line below or anything below it, difference. If you cross the line from upper to lower, lower to upper, you cross it, you add. You understand? You add the numbers, it's not the difference of. I will show you. 3.5 centigrams. Now, already you should realize the units of measure don't make any difference. When you're making conversions, you're only working with the prefix. So I put centigrams, and I want to know how many hectograms that is. Okay? What goes above the C, the lowercase c? 2. What goes above the hecta? 2. But did we cross the line to get there? We crossed the line, so you add it. 2 plus 2, this is difficult, drop the class, is 4. Did we go up or down to get there? We went from here to here. We went up. Which way did we move it? To the left. We moved to the left 4 times. So the answer should be 0.00235 hectograms. Good? Good? Practice those. Don't worry, in the lab you're going to be practicing because I have a page of 15 of them you're going to be practicing. But it's always the same. You stay from the line above or any place above it, difference. From the line below or anything below it, difference. You cross the line. You cross the line, you add. If you go up, you go to the left with your decimal. You go down, you go to the right. Are we good? Okay? Now, you have to memorize the units of measure. Grams, liters, seconds, degrees centigrade, that kind of stuff. That's how you do it. And you realize that doesn't make any difference in your conversions. In your conversions, it's the prefixes. Are we good? Okay. Okay. I'm going to erase these. Watch. What's the unit of measure for liquid volume? Don't wait for me to answer. Pause it, think about it, look at your notes, because you took notes on this. What's the unit of measure for in the metric system for liquid volume? Now, you should have said liters, and you are absolutely right. What is the unit of measure for length? And the answer is meters. What is the unit of measure for weight? The answer is grams. What else can it be? Come on. What else can it be for unit in the metric system, unit of measure for weight? Okay, I got you thinking, and you came up with milligrams, didn't you? No, it's grams. There's no prefix on it. You understand? Conversions, we use the prefixes. Prefixes. Got it? So you have to memorize the unit of measure. I'm going to ask you 2 questions on the exam. Units of measure for what? I'm also going to ask you prefix. What do they stand for? What's the letter? Got it? So you have to memorize those. Then I'm going to have you make some conversions. I think I have you making 2 conversions on the lecture exam, and I'll have you making 3 or 4 of them on the lab exam. So you're going to need to know this. Okay, this is your bread and butter in your future. Okay, over here. You can't see it. Hold on. Hold on. That's pretty cool, huh? Okay. We were working off this list. We just did the prefix. We did the units of measure, base 10, English Imperial System, SI, Systems International. Next one we see is scientific notation. Okay? Now, for scientific notation, what is it? What is it? What is the scientific notation part of the SI, Systems International? Is scientific notation part of the metric system? No, had nothing to do with it. Can I put feet and inches in the scientific notation? I sure can. So what is scientific notation? Some of you are probably saying, I want you to pause. Some of you are probably saying, well, it's the way of taking big numbers and making them small. Okay, let's do that. Here's a big number. 23100165792. That's a big number. Can I put that number in scientific notation? I sure can. Okay, then what is the form for scientific notation? It is the first whole number goes in the box, followed by a decimal place, by any other whole numbers, followed by a time sign, 10, and an exponent in that box. That's scientific notation. First whole number, followed by a decimal, followed by any other whole numbers, or significant number, not whole numbers, significant numbers, times 10 to an exponent. The exponent is how many times you moved the decimal place. If you move the decimal place 3 times, 3, it's 10 to the third. If you move the decimal place 1,000 times, it's 10 to the 1,000th. Do you get it? Okay. So, I'm going to change to black. This number, I'll put commas in here so you can see the number. 23 trillion. Yeah? How much money they gave in stimulus package. How can I, the question was, I said, what is scientific notation used for? You said putting big numbers and making them smaller. I said, okay, can you put that number, that's a big number, into scientific notation? Well, yeah, you can. 2, box, decimal place, 3, 1, 0, 0, 1, 6, 5, 7, 9, 2, because those are all significant numbers. Times 10, how many times you move the decimal place over? 3, 6, 9, 10 times. To the 10th power. So you put that number in scientific notation, didn't you? Only problem is you made it bigger. You're saying, oh, well, we'll just round that off. Okay? Can you round this number? Oh, yeah. Yeah. You can round this number to 2.3. How many significant? Let's just go to 1. Okay? So you take these numbers and you round them off. 2 doesn't do anything to that 9. 9 makes that an 8. That 8 makes that 5 a 6. That 6 makes this 6 a 7. That 7 has no effect on that 1, so it's 0, 0. So it's 2.31. You're going, hey, I rounded it. What about if that's your dang bank account? And you just told everybody, go ahead and knock off $165,000 of my money. All of a sudden, them numbers mean something, don't they? So can you round that number? Nope. That number that we originally wrote, 23,100,165,792, that 2 out there, somebody measured. So it is significant. Do you understand? Now let me go back to my original question. What is scientific notation? Is it making bigger numbers small and smaller numbers big? You're starting to say, well, no, it has to have a bunch of zeros. So it's management of zeros. That is the true statement. Write that down. Put an asterisk in your margin. Scientific notation is the management of zeros. Now let me show you a number that we put into scientific notation. Here it is. 2.3. That isn't what I wanted to do. 23,000,000,000,000,000,000,000. And that's a big number. Can I put that in scientific notation? I sure can. 2 goes here. That 2 goes there. This 3 is the only significant number that we have. 3 times 10. And then the decimal place here, how many times am I moving? Let me put some commas here. So we went 3, 6, 9, 12, 13. 13. That didn't look too good. That looks worse. Let me try that again. Gotta stop using my thumb. I'm going to say 3, 6, 9, 12, 13. Okay, this number and this number right here are the same. 2.3 times 10 to the 13th is this number right here. Management of zeros. You see. Okay, hold on, thirsty. Got to have a little hit of rock star here. Don't do this. This stuff's terrible for you. Don't do this. It's terrible for you. You know what'll happen? You'll lose your hair. Okay. Now, let's use a small number. How about this one? 0.00000000123. That's a little number, huh? But it's got a bunch of zeros out here. Can I put that one in scientific notation? The answer is, man, if I'm trying to manage them zeros, I can do it. What is the rule? First whole number, 1, followed by a decimal place. What are the other 2 numbers? Now there's 2 of them. 2, 3 times 10. Now, if it's a small number, we're going to move it. How many times did I move that decimal place to get it right over here by the 1? 1, 2, 3, 4, 5, 6, 7, 8. Minus 8. So this number is 1.23 times 10 to the minus 8. Okay? Now, mathematicians, chemists will tell you if it is a large number, you move the decimal place to the left, it is a positive movement. Okay? If you move the decimal place to the right, it's a negative movement. So your exponent is negative. If it's a large number, you're moving it the decimal place to the left, it is a positive movement. It's a positive exponent. And whenever you have a positive, you don't have to put it up there. So that 13 actually had a positive in it. We just don't have to put it if it's positive. The only time you have to put it up there is if it's negative. Okay? Now watch the way we do it here in anatomy. If it's a small number, it's a negative exponent. If it's a large number, it's a positive exponent and a subject. Okay? Now, one last step. Can I take this and multiply these two together? Here, I'll do another one for you. Let me erase this for you. Okay. I'm going to use two colors here. I'm going to use blue. I don't know if you can see it, but I'm going to use orange. So I'm going to write this number down here. 2, 3, comma 1, 0, 0, comma 0, 0, 0, comma 0, 0, 0, comma 0, 0, 0, comma 0, 0, 0. What is that number? It's a big number. Okay, and I want to multiply it times a real small number. I want to make that number. I want to do that this way. Point 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3. Now you've been probably taught that if you have a decimal out in front, you have to put a 0 out in front of it to hold it place. If you want to do that, that's fine. It really doesn't make any difference. Okay? Now, I want you to multiply those two together. You're going to go, man, there's not enough board space for us to do that. So let's take and put those numbers in exponential form, in scientific notation, then multiply it. So this one is 2.31 times 10, 3, 6, 9, 12, 15 to the 15th power exponent. Let's take this one and put it into scientific notation. 1.23 times 10. How many times I move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Minus 10. Okay? So what I'm really going to do is multiply these two numbers together because they're easy to manage because they're an exponent. They're in scientific notation. Here's how you do it. Change in color to green. That's black. That's red. That's green. So don't worry about the exponents. Just multiply the raw numbers. 1.23 times 2.31. 3 times 1 is 3. 3 times 3 is 9. 2 times 3 is 6. 2 times 1 is 2. 2 times 3 is 6. And 2 times 2 is 4. And then 1 times 231 is 132. 3, 11. Some of you guys got to do this with a calculator. I can still do it with my brain. 12, 13, 14, 3, 8, 2. 4 decimal places, 1, 2, 3, 4. The answer of multiplying 2.31 times 1.32 is 2.8413. Got it? That's it. I multiplied this times this, and that's what I got. Okay? Can I move that, like 3 makes this a nothing and that makes that a nothing, so wouldn't it be the same as 2.84? No, it's not the same. Okay? Times 10. Now, whenever you have exponents, negative and positive, it's the difference of. If it's positive and positive, you add. If it's positive and negative, it's the difference between. So if you have negative 20 and positive 10, there's going to be a negative 10. If you have a positive 20 and a negative 10, you're left with 10 left over, positive. Got it? So whenever you have exponents, it's the difference of. Okay? So we have a negative 10, a positive 13, that leaves you with a positive 5. And there's your answer of it multiplied. Do you see? Okay. Now, if you have questions on this, this isn't working for you. Work at it first. I'm going to introduce now. I'm going to shut off the video, the recording. I'm going to start up another video, and I'm going to be standing here with a piece of paper in my hand, which is your lab. And it says the lab metric system. Okay? I'm going to explain how to set you up on that. Are we good? Okay. If still you can't get it, and a lot of people struggle with this because they make it more difficult than it is. And some people, as soon as you say it's numbers and it's math, you go, hey, I ain't got that. Okay? Brooke is doing tutoring. Brooke is doing SI. She's already got this hammered out. She will help you walk through it. That's her job. Got it? Okay, so what's going to happen now, shutting this video off, this recording, and I'm posting it onto Canvas. And it'll be posted as metric lecture. Okay? Then this video is going to come on. The board's going to be erased. And now I'm going to stand up here and go through the lab for you, the metric lab, on what I want you to do. Are we good? All right, here we go.